Hello, Chem 111. This video is a follow-up to the initial MO correlation diagram video. This one tells you how to use those diagrams to learn something about bond order in diatomic molecules. So to start with, we need to define bond order, and it's a really easy definition, so I'm just going to define it by example. So if the bond order equals 1, that is a single bond. And if the bond order equals 2, that's a double bond. And I'm not even going to finish this. I bet you can guess what the bond order is for a triple bond. So bond order tells you how many bonds there are between those atoms. And spoiler alert, there may be some bond orders that aren't integers, and that probably won't horrify you because you've already thought about that in terms of resonance structures. This is a little different way of thinking about it. So I'm going to go through an example about how to use the MO correlation diagram to calculate bond order. And I'm going to do it with the question, which has a longer bond, N2 or N2 plus. And before I do that, I want to tell you what the formula is to calculate bond order. So to calculate bond order, it's a very simple formula. Bond order, which has the hilarious initials BO, is equal to 1/2 times the number of electrons in bonding MOs minus the number of electrons in antibonding MOs. Okay, so that's the formula that we use. So to use this formula, we need to see where our electrons are. And even though we did N2 on the last video, I'm just going to do it for you again. So we have, remember in our correlation diagram, we have N on the sides, and we have N2 in the middle. We have at higher energy our nitrogen atom 2p orbitals, and at lower energy, we have the 2s orbitals. And the molecular orbitals for N2 that are built in the middle, we have the sigma 2s, sigma star antibonding 2s. And then here for nitrogen, we have the lowest energy 2p orbitals are the bonding pi 2p. And then we have the sigma 2p. And then we have the pi star 2p, two of them, and we have the sigma star 2p. I'm not going to draw the lines connecting them here because that just gets a little confusing. Okay, and then remember, nitrogen has its 5 valence electrons, so we put those on the side, right? Those are the pictures of the atoms. Now we take all 10 of those electrons and put them into the middle. So we put 2 here and 2 here. That takes care of the 4 electrons from the 2s. And then we have 6 electrons left. So we go 1, 2, 3, 4, 5, 6. Okay, so we did that in the last video, just reminding you that's our electron configuration. So now let's calculate the bond order. So for N2, the bond order is equal to 1/2. So how many electrons are in bonding orbitals? I'm going to actually color code this so we can see them. So I have 2 electrons here in the sigma bonding 2s. I have 4 electrons in the pi bonding 2p and 2 electrons in the sigma bonding 2p. So that gives me a total of 8 electrons minus, and then how many electrons do I have in antibonding? Well, I only have these 2. The only antibonding orbital that's occupied is the sigma star 2s. So I'll subtract those off. And the bond order of N2 is equal to 1/2 times 6, or 3. The bond order of N2 is 3. Okay, and that shouldn't shock you because the Lewis structure that we draw for N2 in fact has a triple bond. Okay, excellent. So before I move on and compare to N2 plus, I just want to note something, which is when a subshell, and this is particularly relevant to the 2s, is completely filled in both atoms, the MOs derived from that subshell don't contribute to the bond order. And then I'll say what I mean by that in a second. And I'm taking time to say this just because it makes our diagram a little easier to draw. So what I mean is that because the 2s orbitals were completely filled here, we had 4 electrons to put in, and that means we put 2 here in the bonding and 2 in the anti-bonding. So we subtract off, in the bond order formula, we subtract these off from these. It's the same number of electrons. So the total contribution to the bond order is 0. So as an example, if we ignore the MOs from the filled 2s orbitals, and I'll just remind you that the MOs from the filled 2s orbitals here are the sigma 2s and the sigma star 2s, then our bond order would equal 1/2, and we would see, oh, we have, so we're ignoring those, we have 2, 4, 6 electrons in bonding orbitals, and up in the 2p section, we actually have 0 in antibonding. And that gives the same number as when we included the 2s orbitals over here, and that's because the sigma star and the sigma canceled each other out. So why that's relevant is that we can often draw, in fact, your book does this, relevant because if the 2s is filled, and so that's any elements in the p block, we typically just draw the 2p section. So as an example, I'll just go ahead and I'll redraw the nitrogen correlation diagram. So we would just redraw it as N and 2, and we would just look at the P because the 2s is filled. Now, if you're over in, like lithium over where things aren't filled in the 2s, then you can't do that. So we have 2p, we have our orbitals look like this. I'll go ahead and label them. Pi bonding, sigma bonding, pi antibonding, pi antibonding, and sigma antibonding. And again, for nitrogen, there are 3 electrons in the p orbitals, gives us a total of 6. 1, 2, 3, 4, 5, 6. Okay, so this is how we would often draw that diagram. Okay, so the question asked us about N2, and I believe N2 plus. Is that what I wrote? Yes, okay. So just as a reminder, we calculated above that the bond order for N2 is equal to 3. So how do we make N2 plus? Well, to make the molecular ion N2 plus, first draw the correlation diagram for N2, which we've done, and then in this case, we're going to remove 1 electron from the molecule. So I like to just go to the middle section, and which electron will we remove? Well, we'll remove the highest energy electron. So it actually could be either of these 2. So I like to just sort of circle it and show that I'm going to kick it out of the molecule. So it's no longer in there. If you want to actually go ahead and draw the correlation diagram, so N2 plus, the reason I like to do it the way I did above is I don't really like to worry about when I put 2 atoms together, like, oh, where did the electron get lost from? It didn't really get lost from the atoms, it got lost from the molecule. So I prefer to just do that. So again, my nitrogens would have 3 electrons, and my N2 would have one of them removed. And so maybe I would like put it up here, flying away with wings. Okay. All right, so the bond order. Bond order for N2 plus is equal to, well, it's 1/2 times. We now have 1, 2, 3, 4, 5 electrons in the bonding 2p orbitals, and we still have 0 in the antibonding. So this gives us a bond order of 2.5. Right, so that's a half bond order. So the question just asked you, which has a longer bond? Interesting. Okay, so N2 bond order equals 3, N2 plus bond order equals 2.5. How do you decide which one is longer? So bond order, again, it's just like the types of bonds we've been talking about. So remember that a single bond is longer than a double bond, which is longer than a triple bond. And what we've just added here is bond order equals 1 means single, 2 means double, and 3 means triple. So from that, you can see that the one with the smaller bond order has the longer bond. Okay, so that's how we use bond order, and that's how we make molecular ions out of these diatomic correlation diagrams. So I'll leave you with one other question. You can try to answer for yourself and then come back and see my answer. Question: does N2 minus have a longer or shorter bond than N2? Okay, so you're going to want to make an correlation diagram for N2 minus, and then calculate the bond order and compare it to the bond order of 3 for N2. And then you can stop the video if you want now, and you can come back and see my answer. Okay, so I'm going to be efficient here, and actually I'm going to just use my same little framework here and do N2 minus. I'm going to take my electron that flew away and put it back. So now I have N2. To make N2 minus, I have to add an electron. So I'm going to add it to one of these pi star orbitals. I put it there, but it doesn't matter. They're equal in energy. And so now for N2 minus, bond order is 1/2 times, I still have those 6 electrons in the bonding orbitals, but now I have 1 in the antibonding. And so this comes out also to a bond order of 2.5, just like N2 plus. So from these data alone, we would actually predict that N2 plus and N2 minus would have the same bond length. I don't know if that's actually true, but it's a good first approximation.